All right, this is video 4 from our lecture video series from Wednesday, March 22nd, where we discuss how to predict when a precipitate is formed in some kind of aqueous reaction. So the overall process for predicting if a precipitate will be formed as a result of some double displacement of ions in solution is the following. So first, we are going to write out our reactants that are involved. Then we are going to undergo or perform our double displacement. Which again is where I say that our cations swap anions. Once we have identified what cation goes with what anion, we are going to put our product compounds together such that S dot T, they are charge neutral. Then we are going to reference our solubility rules. To determine if a precipitate is formed. And then lastly, we are going to balance the overall chemical equation. So anytime we're going to predict a precipitate being formed, this is kind of how it's going to go. And I do like to do it in this kind of more thorough way where we're looking at the reactants and actually drawing out the double displacement and then building our product compounds instead of just looking at the solubility table, because we're going to need information like this coming up later when we learn about the differences between complete, net, and molecular equations that we can show for reactions involving ions in solution. So let's do an example or a view of precipitation reactions. So for example, predict the products of the following, not precipitation, double displacement reactions. And identify any precipitates that are formed. So let's first look at a reaction between aqueous calcium chloride and aqueous silver nitrate. So we're looking at our two reactions, our two solutions of these aqueous or dissolved ionic compounds. So if we're going to first predict the products, we need to write out the reactants involved, which we have done, right? We have these reactants. And then we need to undergo a double displacement such that the cations swap anions. So the way that I like to do this is I actually like to think about what ions each of these solutes is going to contribute to solution when they are dissolved. So when I have a solution of calcium chloride, I don't have units of Ca with two Cl's stuck to it. I rather have a calcium ion which because it's on group 2 has a +2 charge. And then chlorine ions, specifically 2 of them. And then silver, I know that silver is one of our exceptions to our transition metals. It always forms a +1 cation. And then nitrate, NO3, I recognize that as one of my polyatomic ions, which has a -1 charge. So if we're going to do a double displacement, then the cations need to swap anions, meaning that the chlorine needs to go to the silver, and the nitrate is now going to be coupled with the calcium. So that is our double displacement. So we have written out the reactants involved, specifically the ions that those reactants are contributing. Then we are going to swap our anions. So let's see what those compounds are. So we're up on step 3, put the compounds together such that they're charge neutral, meaning I need to look at what happens when I try to couple silver with chlorine, how I could put silver and chlorine together so that I have an overall neutral charge. And then also the same with calcium and nitrate. So let's start with calcium and nitrate. So calcium, as we know, has a +2 charge. And nitrate has a -1 charge. So I need 2 nitrates in order to form a compound with calcium that is overall charge neutral. So I write this as CaNO3 wrapped in parentheses 2. And then I'm also looking now at my silver and chlorine. So silver has a +1 charge, chloride has a -1 charge. So I just need these to come together in a 1-to-1 ratio. So AgCl. I have now made it so that my overall products are charge neutral. So we have done step 1. Write out our reactants involved, specifically the ions they contribute. Identify what ions are going to be swapped. Swap your anions. And put your compounds together. So product compounds must be charge neutral. And up next, we need to reference the solubility rules to determine if a precipitate is formed. Meaning we need to now look at calcium nitrate and silver chloride to figure out which of these are soluble or insoluble. So let's pull back up our solubility rules. All right, so let's see here. I'm going to go fishing for a rule about nitrates since I have a nitrate polyatomic ion. I have a nitrate rule which says that all nitrates are soluble, meaning that the calcium nitrate compound that we formed is going to be dissolved in solution, meaning we're forming just calcium ions and nitrate ions. Or at least we just have calcium ions and nitrate ions. All right. Silver's popping up, and I do remember that being an exception in a lot of my solubility rules, but what I see a given rule for is my chloride ions. So these are soluble except for when we have silver present. So if this was chlorine with anything but silver, lead, or mercury 1, then this would not be something that, then this would be something that is in fact soluble, just like calcium nitrate. We would be able to keep it dissolved in solution. However, because this is one of our exceptions, we create the silver chloride precipitate or insoluble solid product. Okay, so we have referenced our solubility rules to determine if a precipitate is formed. We have one, that is our silver chloride. And up next, we need to balance the overall equation. So let's take a look here. On the reactant side, I have 1 calcium. On the product side, 1 calcium. That seems good so far. But then on the reactant side, I have 2 chlorines, and on the product side, only 1. So I need to double the amount of silver chloride that is made. In doing so, I've doubled not only the chloride, but also the silver. So I need to double the amount of silver on my reactant side. And in doing so, I have also thus doubled my nitrate. And if we look on my product side, I have 2 nitrates. So this is my balanced chemical reaction, indicating my precipitate that's been formed. And I also now have the overall balanced equation that's showing what's happening chemically in this beaker. In fact, I think it's a good practice for us to maybe draw kind of the pre-reaction before our ion association beaker and then our post-reaction beaker. So let's look pre-reaction and then post-reaction. Again, let me draw. I know I'm neurotic about this, even though I'm not very good at it. Okay, so here's our water solvent in blue in each of these reaction beakers, which are the same beaker. It's just we're showing one at one moment in time versus another, specifically before the reaction happens versus after. So I need to consider what is going on inside this beaker before my ions have associated together. So since I have already looked at what is going to dissociate, I already know what ions are going to be present. But now I just need to take into account the fact that I have balanced my equation, which is going to change the relative proportion of each ion that's present in solution. So I have 1 calcium chloride, which is going to put in Ca2+, and then 2 chloride ions. And then I have 2 silver nitrates, so I'm going to generate 2 silver cations and then 2 nitrate anions. Okay, as a result of my double displacement, I'm going to see now association between my silver and chloride ions as well as my calcium and nitrate ions. And we used our solubility rules to determine if that association results in the formation of a precipitate or a solid or an insoluble product. Those all mean the same things. And we found using our solubility rules that we actually form silver chloride, which is a solid. So I'm going to write AgCl solid, and I make 2 of them. So I would actually see some kind of solid forming. Okay, let's see if this works. I don't know if it will. Nope, did not work. Perhaps this will work. So this is our solid that we form, our precipitate. And then we would have our aqueous or still dissociated, still dissolved calcium and nitrate. And let's do some counting of ions to make sure that we're following the law of conservation of matter. So both my silvers and my chlorines have become solids, meaning that I now am going to look at the association between calcium and both of my nitrates. However, that association does not form a solid, right? It creates just another soluble ionic compound. So I've still got Ca2 plus and nitrate left over. So again, always putting yourself in the perspective of the beaker is going to help you think about what's happening here. Okay, I'm going to split this particular section up into two. Let's do another example when we come back. So take a break, and then we will look at another example of precipitate formation potentially. And that will be it for today.